Welcome everyone to the second session of today. I'm Georg Schildbach, I'll be the session chair, and this is Daniel Axel, and he will be the co-chair of this session on vehicle control. I think we have a very interesting program for the next hour with 4 presentations on emergency maneuvering, drifting and heavy vehicles, and a lot of advanced control concepts. So it should be an interesting hour. We're still missing the third speaker, so if the third speaker could come up and get registered, that would be nice. And also if Nicole Morgowski could come and talk to Jonas Stjurberg, that would be great. Thank you. So without much further ado, I'm going to introduce the first speaker today, Boyang Yi from Opel, and he's going to talk about real-time integrated control and trajectory planning with MPC for critical maneuvers.
Thank you. Yeah, thank you for the nice introduction. I'm glad I'm here and that you are here. After a small meeting, and I will promise I give a very simple to understand presentation so that you can follow. My name is Boyang Yi and I'm with Adam Opel AG. I presented some work with my co-authors from Opel and Karlsruhe, and the topic is about MPC for integrated planning and control. Just get into the agenda. I first talk about the motivation for collision avoidance control, then I will explain why we have a closer look at integrated trajectory planning and control, give a short introduction into MPC for those who don't know this, and explain our approach for this problem. Then we'll show you simulation results and summary. So first, the motivation. Imagine you are driving in a city, in an urban area, and before you can react, there might be some obstacles in your way. You might need an assistance system to help you avoid the collision. The scenarios that we have to look at is an urban environment, for velocities for 30 to 70 km per hour with maneuvers where we have small lateral offsets. And the topic I present is for these scenarios, the vehicle dynamics control algorithm and plan. Let's get into why we want to have integrated control. First, we have a look at the classical controls concept where we have 2 modules. First, where the trajectory planning calculates a trajectory according to some geometric equations, and then the vehicle dynamics control keeps the vehicle on this track. There are some properties I want to mention here. First, this classical control is calculating a fixed trajectory. This might not be suitable to handle dynamic scenarios. After we have started the maneuver, next the trajectory is often defined in many works by geometrical equations, which might not consider vehicle dynamics, and also the control characteristics defined by tuning work. That's the motivation for integrated control and trajectory planning, where we hope to have several advantages. The property is that we have 1 module instead of 2, and the advantage is that we can update the trajectory at each control step. The trajectory is calculated and calculated and planned with vehicle dynamics, so it's the trajectory generation considers vehicle dynamics directly, and the trajectory considers control characteristic also, so that we don't need to tune the control separately. Yeah, there have been a lot of work that's doing this, and the focus of these works were trajectory planning and control for steering-only maneuvers, where the prediction is not done for the braking part, and what we are doing in this work is to investigate trajectory planning and control for braking and steering maneuvers, and also we show how we can do this in real-time application. Or potential real-time application. So let's just get into the theory of MPC. For those who don't know it, the MPC considers a time horizon in front of us where we have given a reference trajectory that we want to follow. We discretize the horizon, with some discrete time steps, and then we calculate some predicted command signal sequences, which, when applied, we can get a predicted trajectory that follows the reference. And this is done by by solving an optimization problem where we try to follow the reference trajectory. So we will try to minimize the predicted and the reference trajectory for the horizon steps. And we have, in a very simple version, a linear state space model, which represents the behavior dynamics. And after this is done, we apply the first value to the system, and when time goes by from T0 to T1, we will calculate another sequence and apply the first one, and this goes on and on. So let's go into the topic, how we use this MPC for our problem formulation, what our problem formulation is. We want to do collision avoidance control and trajectory planning by combined braking and steering, and we defined an optimization problem which will try to minimize the yaw angle, the velocity, and the command signal. As we have heard in the morning, it is advantageous to reduce the velocity during collision avoidance maneuvers, and that's why we are doing here. Also, we have some constraints that we need to consider. First, we have behavior dynamics. I will not go into detail, just shortly, I'll use a single track model with tires and also a suitable model for the longitudinal dynamics. We have to consider stabilities, boundaries, stability envelopes. We, of course, want to avoid a collision, so we have a constraint for the position. We have actuator limitations. We want to consider friction limits by friction circle or friction ellipse. And we also need to consider road boundaries, so the lane to the left or the right. And we did two versions of this MPC formulation. One in an ID MPC formulation, where we formulated a nonlinear optimization problem. I will go in some detail later, but not go too deep here. The problem with this is that we have high combination complexity, because we have nonlinear constraints and models that we need to consider when solving this problem. And what we did in the next step is to use approximations, linearization, simplifications, and to define a quadratic program to solve this problem. And we will show later how we can reduce the combination complexity with linear constraints and models. One of these constraints I want to explain more in detail, and this is the collision avoidance constraint. Imagine you are in the situation where you have an obstacle here in black with a given distance and width and position. We assume that the sensors here are exact, which in reality is not, but for this simulation environment it's okay. We try to get a trajectory or a control sequence that will give a trajectory that gives this, that will result in these predicted positions. So for the nonlinear control, for the nonlinear optimization problem, we formulated a constraint that looks like this. There's an if-else structure. If the predicted position in the corresponding prediction time step is in front of the object that we want to avoid for, then we consider for the evasion only the right lane. And if the predicted position of the vehicles is reaching the obstacle, then we consider, of course, the obstacle width and position for the evasion. And yeah, this constraint is hard to solve very fast because it's nonlinear due to the if-else structure. But what we did in the next step is to use linear inequality constraints. How we did this, I will show you in the next slide. But the advantage of this is that it's linear and you can use efficient solvers for it. And what we reach with this technique is to decouple of lateral and longitudinal position for one time step for collision avoidance. So now we come to how I did this linear inequality constraint. We have the equation here above, and this situation here where we have predicted longitudinal positions of the last control step, and we have an obstacle here, and what we do in this step is to give an y-ops vector of obstacles, or vector of minimum lateral deviation that we want the position to satisfy. And we see for the last two prediction steps, we have the y-ops, so the obstacle width, and for the other one we consider only the right lane. And if we solve the optimization problem for this step, we will get a trajectory where the longitudinal position for each trajectory time step will deviate, because the lateral and longitudinal position are also states in our vehicle dynamics model. And due to this deviation, we will update this vector and get an updated minimal lateral deviation for each time step. The assumption that these techniques work is that the control step is then very fast, so should be less than 100 milliseconds. And we will show later that we satisfy this. Then we get another trajectory which might look like this, and we will do this after each control step. So let's get into some results in the performance and simulation. We see here the vehicle dynamics states, the driven states, the driven trajectories, and states for one scenario where we have this obstacle here and start triggering the control around here, at here, and okay, at here. And we see that the NPC, so this is the ideal formulation, the approximative formulation, MPC algorithm, they have similar performance. They both reduce the velocity to 0, and the curves are matching very well. And this can also be seen from the criteria we chose. For collision avoidance, we have criteria to have low lateral end position, because we don't want to endanger too much other participants. We want to reduce velocity, as this is good for insurance reasons. And we see that the criteria are similar, and we have median computation time. We have a big improvement on median computation time. For the ideal formulation MPC, we have 5 seconds per optimization step, which is not real-time applicable. And for the approximative MPC, we have 10 milliseconds with the hardware I gave here. So this is only simulation for here. Next step we are about now to do this in real time on test vehicle, but I have not prepared results here. So now I prepared some videos to demonstrate the performance in simulation environment. We have on the left a mechanical environment where we're driving on a static obstacle and trigger the event at a given PDC. And on the right, we have the predicted command signals and states that the MPC calculates for each time step. And we can see, when I start the video, how he predicts and plans a maneuver. I will show it again. You can see that there was a black obstacle that is approaching us when we are driving to the static obstacle. I will show it again with a slower speed. We can see that we try to brake the system to zero velocity, and I hope you saw this obstacle also. And then I have another video prepared where I extended this algorithm for another scenario where we have 3 obstacles, and this example is just to show that we can extend this algorithm very easily for other maneuvers. In this maneuver, I removed the velocity cost function so that it does not break. And we can see that here on the right we have the predicted trajectories for each position, for each time step, and the driven trajectory, as well as the predicted trajectory for each previous path step. We see that at the time when the prediction horizon gets a new obstacle, we replan the trajectory and get another, catch another trajectory, and so that we can handle dynamic scenarios, which was one of the motivations of integrated control and planning. Now coming to my last slide, what have I shown here is a method for integrated vehicle dynamics control and trajectory planning by combined braking and steering. I showed two versions of it. First, ideal MVC formulation with non-linear optimization, where the advantage was to generate trajectories and considering vehicle dynamics, which is able to adapt to dynamic scenarios during the maneuver. We have less tuning of control parameters. And the next version, what I showed, this approximative MVC, where I showed how we can do this with comparable performance, but with extremely reduced computational cost. And it shows potential for real-time application. The next steps are to apply it in a test vehicle and to show that it's really real-time applicable, and also to compare it with other classical, with the classical concepts of state-of-the-art trajectory planning and control concepts, and see how it compares.
Okay, thank you very much.
Yeah, thank you. This was the last slide. Thank you for your attention. This was superficial explanation of the topic. You may ask questions here or later in the poster session.
Okay, so we have time for a quick question while the second speaker prepares.
Hello, thank you for this presentation. Did you take into consideration the speed of the steering wheel in the constraints?
The speed of the steering wheel?
Yes.
Yeah, there should be, in this actual limitations, we have the steering wheel rate that we consider, the angle rate that we consider.
Okay.
In this part.
How much is the value that you consider?
The derivative of steering wheel 300 degrees per second, something like this.
Okay, thank you.
Okay, so let's thank the speaker again. For a second talk with the title Coordination of Motion Actuators in Heavy Vehicles Using Model Predictive Control Allocation. And this is presented by Andrea Sinigaglia from Chalmers University of Technology. Please go.
Good morning, everyone. As he just said, I'm Andrea Sinigaglia. Here in the slide, you can see the other people that work within this project. Christopher Tagesson, Paolo Falcone, and Bengt Jakobsson. The project has been carried out at the Volvo Group Trucks Technology in collaboration with Chalmers University of Technology. To address the topic of the project, I would like to focus a little more on the title. So today we are going to talk about control, and in particular about control to coordinate different motion actuators in vehicles. Specifically in heavy vehicles, using a method called model predictive control allocation. I would like to start pointing out what is coordination and why it is important. Recently, vehicles have been equipped with more and more motion actuators, independent disc brakes, rear axle steering, engine brake, but also active suspension, electric motors, and so on. Usually, all those actuators simultaneously compete to modify vehicle dynamics. When considering different actuators, it is important not only to be aware on the way each actuator modify vehicle dynamics, but also on how its actuators respond to a stimulus. That is, on what is the dynamics of each actuator. For all this reason, it is today important to have an effective coordinator in a vehicle. We focused our attention in heavy vehicles, in a vehicle like the one you can see in the picture, that is an overactuated vehicle. In this vehicle, we could control disc brakes independently, rear axle steering, and engine brake with a method called model predictive control allocation. The method is optimization based, and in particular it is based on the minimization of a quadratically cost function with linear constraints. The method is the diffusion of two other control theories or two other methods, control allocation and model predictive control. The control allocation itself is an optimization-based method, and it is useful in situations like the one you can see in the picture. That is why I want to perform an action on a system like moving the box, and in order to do so, I can count on one or more motion actuators. When more than one actuator can perform that action, control allocation assures that the use of the actuators is optimal by some index. As we want to control different motion actuators, we have to include the dynamics of the actuators in the control, and so we borrowed an idea from model predictive control. That is, we introduced a model for each one of the actuator in the control allocation formulations, in the constraints in particular, and we added a time horizon in the cost function. This is the workflow we have followed during the project. So all the simulations were performed in Simulink with the vehicle model provided by Volvo Group Trucks Technology. The controllers themselves were developed in Simulink, and to solve the optimization problem at each step, we used a software called CVXGen. Regarding tests, we used the DSpace suite to transfer the controller from Simulink to a prototypal ECU, a Micro Autobox 2. As vehicle, we used a Volvo FMX at the Hellared Volvo test track to the test sessions. To evaluate the performance of the controller, we set up 3 different scenarios. A braking event on an asymmetric road, an acceleration from standstill on an asymmetric road, and a braking event on a normal road that blends the use of disc brakes with engine brake. Among these scenarios, the last 2 were only simulated, while for the first one we made both simulations and tests. As I'm going to show you the results from the test sessions, I would like to introduce you the idea of a split mu braking event. As you can see, we have a vehicle where one side of the wheels are in contact with a low friction coefficient surface, while the other side of the wheels are in contact with a high friction coefficient surface. The idea is to use the vehicle on the left, in this case, to generate the majority of the braking force needed to stop the vehicle. As this would introduce a yaw disturbance in the vehicle, we use the rear axle steering to correct the yaw moment and keeping the vehicle straight. As brakes has a much faster response than rear axle steering, the coordinator has to be aware of the dynamics of the 2 actuators in order to have an effective control. At Hellared, we used a surface of wet basalt to simulate an icy road, while on the other side of the vehicle there was normal asphalt. The objective for the driver was to stop the vehicle while keeping it on a straight path. As you can see in the graphs, on the left the steering wheel angle during time, on the right the vehicle speed during time. The vehicle stopped in a reasonable time without asking any demanding intervention at the driver. It has to be said that in all the simulations and tests, the priority was to avoid yaw disturbances in the vehicle, and this was a little the stopping distance of the vehicle, but this trade-off can actually be dynamically adjusted during the computation, so you can decide which is more important. Here it is interesting to see how the actuators behaves. You can see on the left the brake pressure on the two sides of one axle, while on the right the rear axle steering wheel's angle. It is interesting to see how the algorithm itself recognizes the advantage of braking unevenly on the axles of the vehicle, while at the same pace growing up the steering wheel's angle, the rear steering wheels. After we have proved the behavior of the controller with the model predictive control allocation method, we wanted to compare it with its simpler version, that is the control allocation. Here you can see in blue the model predictive control allocation, in red the control allocation method. On the left, the commanded input to the rear axle steering. On the right, the actual output of the rear axle steering. Because control allocation does not have an explicit model of the actuators, it has to be set some rate constraints in order to have at each time step that the actual output of the actuators are as close as possible to the commanded input. As a consequence, the rear axle steering wheels takes more time to reach their steady state value. As a further consequence, the brakes have to wait a little more before they can reach the steady state value, and here you can see the acceleration of the vehicle during time. The vehicle during the initial transitions take more time to reach the desired deceleration. We performed various sessions, and actually this is something that was repeatable, and so that it was proved to be like that. I would like to conclude and sum up. So today I've introduced the importance of having a coordinator in a vehicle. I introduced a method called model predictive control allocation compared with another method called control allocation. Both method performs fine in the sense that both methods do what expected by the developer. And maybe it was not clear from the presentation, but both methods are very scalable, and they can be adjusted to many different vehicle configurations. When compared between each others, model predictive control allocation can fully exploit the actuators, and so it performs better during transitions. This comes to a cost that is a higher computational time to solve the optimization problem at each step. That is actually an advantage of the control allocation method. If you have any question, you can make it now, or you can reach us after lunch at the poster session here. And thank you.
Thank you very much. We have time for 1 or 2 questions. No questions? Okay, so then, thank you very much again.
Thank you.
Okay, so the next speaker is Jonathan Goh from Stanford University, and he's going to talk about simultaneous stabilization and tracking of basic automobile drifting trajectories. Welcome.
Hello, everyone. I'm John. Thank you for the introduction. I'm from the Dynamic Design Lab at Stanford University, which is led by Professor Chris Gerdes. I'm here today to tell you a little bit about the stabilization and tracking of some basic drifting trajectories. So why do we want to study drifting in the first place? As many of you may know, modern cars today have electronic stability control systems, and this intervenes when necessary in order to keep the car within stable handling limits. For example, if you're making a left turn a little bit too quickly and the car starts to over-rotate, it might apply brakes to the front right wheel in order to prevent the car from spinning out. One sort of readable way to think about these stable handling limits is in terms of the vehicle's yaw rate and side slip. Side slip is the angle between the car's velocity vector and its longitudinal axis, which is indicated here by the symbol beta in green. Using models of vehicle dynamics and models of tire friction, we can come up with a region of side slip and yaw rate within which we expect the car to be open loop stable, and outside of which we expect the car to be open loop unstable. Normal driving takes place well within these limits. Some of our other work has looked at autonomous racing, and there we want to go around the track as fast as possible. And to do that, we actually have to go right to these limits and try to stay there. So you could hear in the steady state part of that corner that some tires squeal, which is a good indicator that we're really right at the limits during that turn. Some of our other work has looked at obstacle avoidance in the case of emergencies. And we've seen that it's oftentimes actually necessary to temporarily leave this area of guaranteed open loop stability in order to avoid the obstacle, and then just come back into the stable envelope later on.
If a car is physically capable of avoiding something, we'd like to develop the controllers that can make that happen.
Once again, the high amount of tire squeal is a good indicator that we're doing a pretty extreme maneuver. And tire squeal is a metric I will continue to use in this presentation. So this is actually similar, though a little bit less extreme, than to what some of the very best human drivers are able to do when the situation might demand it. For example, a professional rally driver will often purposefully flick the car around a corner. But neither of these maneuvers are allowed by ESC, which prioritizes stability over all else. This makes sense for average drivers. I will be the first to admit that I'm an average or possibly worse than average driver, and when faced with an unstable situation, I don't usually do very well. Trust me, I've tried. However, we believe that autonomous cars shouldn't just be average drivers, they should be as good as or better than the best human drivers. So autonomous cars should have mastery over all operating regimes and not just the easy, open-loop stable ones that ESC gives us. And drifting is actually a pretty good way to study this. It takes place far outside these stable limits where the dynamics are both unstable and quite fast. Yet we know that really good human drivers are able to not only stabilize the car, but also perform very precise positioning. You can see the driver just put the back end of the car right around this concrete barrier while drifting around at high speed. That's very impressive, and I think autonomous cars should be able to do that if the situation might demand it. So what exactly is drifting from a more sort of formal vehicle dynamics perspective? Like a lot of interesting car phenomena, this actually comes about because all maneuvers that a car does is going to be limited by the amount of friction available. One very simple model for this is the friction circle, which simply states that the vector sum of lateral and longitudinal force on a given tire is going to be limited by mu times Fz, the normal load on the tire. So the more you accelerate or brake, the less force you have available to do any turning with. When you're going around the turn, the tires are generating lateral forces that keep you on that turn. And if I apply enough throttle to the rear tire, it reduces the amount of lateral force the rear tire can give. And if I really just push the throttle down, the car starts to spin. It is now unstable and will continue to spin out unless corrective input is applied. This is the open loop unstable region we talked about earlier. So drifting then is actually the art of balancing this unstable equilibrium while trying to track a path at the same time. So now that we know a little bit about what drifting is, we can start to look at some controller design. I won't go into sort of too many of the mathematical details here, but I want to try and sort of capture the major takeaways. So the first sort of interesting thing has to do with inputs while you're drifting. It's actually quite different from normal driving. Steering is the same. We still control the front lateral force by using steering. However, because the rear tire is now fully saturated, it is on the friction circle itself, which means we can actually take this constraint and invert it, and now have a direct mapping from throttle to the rear lateral force. This actually, I think, is a pretty interesting point in and of itself. Your rear lateral force is no longer a sort of complex, nonlinear function of your tire model and your vehicle states, but something you can control directly. So that's pretty cool. The other interesting thing, in my opinion, is our choice of control objectives. In order to track the path, we use the look-ahead error, which is the lateral error from the path tangent of the vehicle, propagated some distance forward along the car's velocity vector. This is akin to a weighted sum of the lateral error and the lateral error derivative, so it's basically PD control, but represented in perhaps a more sort of physically meaningful way. The other objective we're trying to track is the side slip beta. This is also the final objective we're trying to track. So this might be alarming to some of you that we're not trying to track outspeed at all, but I want to assure you that this actually will happen as a byproduct of tracking both the side slip and a path. So now we have our inputs and we have the objectives we want to accomplish. We can try and create a controller by very simply imposing stable first order dynamics. We use a simple two-wheel bicycle model and a brush tire friction model as our vehicle model. And the resultant controller actually has a very simple form. You use the total front and rear lateral force, FYF and FYR, to accomplish your path tracking objective. And you use the difference between the front and rear lateral force to track side slip. And this difference is akin to sort of a yaw balance on the car. This has two equations and two unknowns, and we can solve for a unique FYF and FYR value. And then we can map the front lateral force to steering by inverting our tire friction model. And we can invert the rear lateral force into a throttle input based on our friction circle. This actually means that steering and throttle must be precisely coordinated to simultaneously track both the path and side slip while you're drifting. This is quite different from normal driving, where we often sort of assume decoupled dynamics, where we can use the steering to track the path and use the throttle to track the speed, and do those kind of independently of each other. Specifically, when you're drifting, as you steer out of a turn and you're trying to increase the turn radius, you actually need to also apply more throttle in order to keep the car balanced. And when you steer into a turn or reduce your turn radius, you have to sort of reduce your throttle input to keep the car balanced. This can create some sort of, I think, somewhat counterintuitive situations. For example, pretend you're the driver of this car right here. Right now you're too close to the cone and you're pointed straight towards it. Your instinct might be to steer away and probably also lift off the throttle so you don't head towards the cone. However, if you did that, you would just spin out. And the right answer is actually to apply more throttle while you steer away. So I think this is pretty counterintuitive, to be looking at the thing that you don't want to hit and also have to apply more throttle. So I think this is something that a naive controller, or indeed a naive driver, would have some difficulty with. Now the part that everyone's waiting for, experimental results. So I'm going to show you this video of a test. The first part of the test is going to be sort of autonomous, very basic circle driving. And then the drift controller is going to be turned on. And the reference trajectory here is a simple circle. And the side slip demand will ramp from 0 to 45 degrees, somewhat slowly. And then we'll stay at 45 degrees for the duration of the test until we manually stop it. So as the car starts to become more sideways, you can see copious amounts of tire smoke start to develop. You can see more and more tire marks begin to lay down on the test surface. And as you can tell, we did this test a couple of times here. It's a good test of whether we feel sick first or the tires pop. Alright, so early on in the presentation, I used tire spill as a metric for how extreme a maneuver was. I'm just going to bookend that sort of extreme end of the scale by showing you a little clip with audio. So as you can hear, the tire is working pretty hard. You can also see the smoke swinging off the tire, which is also a good indicator that it's being well used. You can also notice the cone is actually quite stable in this video frame as well. So I know the video is hypnotic and the sound is beautiful, but I have to cut it short a little bit here. So now we look at some plots, everyone's favorite thing, and you can look at the controller performance. So side slip is generally held to within about 5 degrees, and even during the ramp maneuver. And lateral arrest is generally within about 30 centimeters. It's a little higher during the initiation ramp, but still generally very contained. And as I promised earlier, the velocity is actually stable and close to the predicted trajectory value. It sort of has this little blip at the start when the car is transitioning to drift dynamics and initiating the maneuver. But otherwise, it stays quite close to the value we had hoped it would take based on our models. So I didn't talk about the trajectory planning or trajectory generation at all, but I actually think that stuff's pretty interesting. And basically is like half of the paper. So if you're interested in that, please come talk to me at the poster session or read the paper, I guess. Cool. So early on in the presentation, I promised that being able to drift would allow an autonomous vehicle to do maneuvers it otherwise might not be able to. So in this example here, it might be a little bit contrived, but here we're going to ask the car to actually perform a turn that's smaller than its minimum turn radius as defined by steering angle limits. So it's going to start at a slightly wider radius and then be asked to spiral in towards the cone while increasing its side slip to about 45 degrees, and then drive around the cone for a little bit and then spiral out while reducing its side slip. And then we stop the test. I want to note that we actually moved the cone from previous testing because we hit it a couple times. So having tried to do that maneuver, I can tell you it's quite hard by sort of manual operation. All right, so maybe a little bit of a contrived example, but also that's all I need really for an existence proof that being able to understand the dynamics and control of drifting would allow us to expand the safe operating envelope of autonomous vehicles. I think we've made a small step towards that. We've demonstrated some tracking and stabilization and actually path generation as well for some very basic trajectories. Moving forward, I think we need to look a little bit more at the feasibility and planning of more complex trajectories. And also thinking more about the control during the transition region between normal driving and drifting, which is especially important for its applications to vehicle safety. So on that note, I want to thank you very, very much for listening and for the opportunity to talk to all of you here today. And I'm just going to let this video play while I answer any questions you might have.
Thank you very much for that. Do we have any questions?
So, thank you, John. It's very good. Have you tried to apply that to motorcycles as well? That would be an interesting application.
To motorcycles?
To motorcycles.
Ooh, that's doubly hard. No, I know people have asked me that before, and I think that's perhaps the next stage, because it does sound a lot harder. Also difficult to test, I think.
But easier models. Okay.
Well, we use a bicycle model here, so I'm not sure it will end up being easier.
More questions?
Thanks for the very nice presentation.
Thank you.
I wonder how well are the trajectories that you control reproducible? So, so you need a couple of turns before you come into the drifting modes.
Yeah. So the tests are repeatable each time, so that you can run the same test over and over again, and it tends to look quite good. I think if you look at sort of I don't have any plots to show you, but if you look at just the thickness of those lines that have been laid down by the rubber, that the path is quite repeatable from one test to another. But you are right in that the tracking is a little worse during the initialization procedure, and that's something that we need to look at a little bit further in terms of understanding sort of the control and the dynamics in between normal driving and when you're fully sort of in the drift. Does that answer your question? Okay, cool. Thank you.
We have time for one last question. Yeah. Yeah.
Thank you very much. When you show us the lateral error, so I would like to know what is the reference trajectory.
For the plot I showed you, the reference trajectory is just a circle. So it's a circle of constant radius, 5.2 meter radius.
And when you convert, I think first you determine the lateral force and you convert it to steering angle.
Correct.
So you need to know like front cornering stiffness. So
correct.
The estimation was done inside.
Yeah, so we did that. We did a ramp steer maneuver, and then we determined offline beforehand what the cornering stiffness and the peak friction and stuff of the tires were beforehand.
Okay, thank you.
Yeah.
I think we have time for one more question. I think we have one over there. So.
Did you have a sensor to detect the position of the cone?
No, so we actually use RTK GPS for all our positioning and for all our dynamic rates. We actually put the cone there, and then we drive up to it until the bumper hits the cone, and then we calculate what the GPS position of the bumper is, and we enter that into control desk, and that's the center of the circle. And then we do a test. That way, it's really easy just to set up the test and move around to different test sites as the day evolves. Because oftentimes we need new tarmac where someone else needs to use one part of the test site.
Okay, so let's thank the speaker again for a very nice work presentation. So the title of the last talk is Non-Linear Lateral Vehicle Control in Combined Energy Steering and Braking Maneuvers. And this is presented by Stefan Hahn from Aschaffenburg University of Applied Sciences.
Yes, okay. So welcome to my presentation, Nonlinear Lateral Vehicle Control in Combined Emergency Steering and Braking Maneuvers. My name is Stefan Hahn, and I'm currently working as a research assistant at the University of Applied Sciences, Aschaffenburg in Germany. And I'm pleased to present you the work of Tobias Brands and Professor Klaus Zindler, and myself. And as you can see in the picture, unfortunately we do not have a DeLorean, but we also got a car. We've got a good old BMW. So, and I promise I'll also show some experimental results at the end. Okay, I will begin with a short motivation, the problem descriptions, and the main contributions. After that, I'm going to describe the plant model on which the lateral vehicle control design is based on. Before I conclude, I'm going to present the experimental results. Well, it's a well-known fact that pedestrians are among the group of the most vulnerable road users. And the reason for this is that a critical traffic situation with a pedestrian can occur in really a very short time due to the movement capability of the pedestrian, which is able to start a motion suddenly or even change its direction towards the lane within some hundreds of milliseconds. And due to the resulting low time to collision, an average driver is often not able to avoid such a resulting collision. So there is a need to develop an autonomous pedestrian collision avoidance system. And this is the main focus of the research project AFUS, which is funded by the German Federal Ministry of Education and Research. AFUS comprises three main components. First of all, we detect the pedestrian's intention to cross the street, and by means of this, we detect a critical traffic situation. After that, we determine the optimal collision avoidance strategy, also by means of the localization of the vehicle within its own lane. After that, by means of lateral longitudinal control concepts, we avoid the collision via autonomous braking and steering. And the focus of my presentation today is on the third component. So first, let's have a look how an autonomous collision avoidance system should react in order to avoid an imminent collision. And the proper reaction depends mainly on two variables. It's here the relative velocity between the vehicle and the pedestrian, and the distance to the vulnerable road user. And by means of this graphic, we can illustrate here four main areas. In the first area, the collision could not be avoided. However, in the second area, the collision can be avoided by steering or braking maneuver. The third area comprises traffic situations which can only be diffused by an emergency steering maneuver. So here, an autonomous emergency braking system helps us to avoid or mitigate a collision. In contrast, in the fourth area here above, the collision could only be avoided by a steering maneuver. And this is depicted here in the graphic. You can see that the vehicle has passed the last point to steer, so the only possible reaction is now to steer. And this is also the central idea of AFUS, where we want to ensure a lane-keeping evasive maneuver in such critical traffic situations. Moreover, there is also a fifth area, which comprises the traffic situations which can only be diffused by a combined steering and braking maneuver. You can see it here in the picture. The resulting last point to steer and brake is the nearest point to the pedestrian. So our main objective is now to develop a control system for combined emergency steering and braking, and today I want to focus on the lateral vehicle control system for these scenarios. And please keep in mind that even if the collision could not be avoided by such a maneuver, we reduce the kinetic energy of the vehicle significantly. So we also significantly mitigate the injury severity. One important requirement for designing a lateral vehicle guidance controller in combined steering and braking maneuvers is the appropriate modeling of the lateral longitudinal tire forces in these maneuvers. And the nonlinear coupling of these forces is depicted in the graphic here below. You can see the normalized lateral tire force independent on the slip angle, and you can see here in the blue curve the well-known degressive characteristic of the lateral tire force in case of no braking. However, in case of braking, and let's say in case of a longitudinal slip sigma x, the lateral tire forces, the transmittable lateral tire forces, are reduced up to 50%. So our main objective is, as I said it before here, to develop now a lateral vehicle controller, and in special for these combined emergency steering and braking maneuvers. And to this, we derived the new vehicle model, including a nonlinear combined tire model, which takes into account this nonlinear coupling. And based on this model, we designed a follow-up controller using the method of input-output linearization, and we also adapted this controller to the present class of a nonlinear system, a nonlinear controller-feed system with time-varying parameters. Okay, now let's have a look on the plant model. The plant model comprises of four main components. The first component corresponds to the vehicle dynamics. And here we got the state variables side slip angle as well as yaw rate. Furthermore, we model the kinematics of the vehicles, and here we model the kinematics of the point to be guided on the path. And in our case, it's the preview point P. It's the middle of the vehicle's front. And due to this, we get the state variables cos angle as well as the y coordinate. Two further states are added by modeling the dynamic transmission behavior of our steering actuator, and we get here the state variable steering wheel angle and steering wheel angle velocity. fourth and a major component of the model, of the plant model, corresponds to the tire model. And the lateral tire forces, Fy, significantly are very important to determine the vehicle dynamics and thus the kinematics. So now let's have a deeper look on the tire model. The main objective of modeling the tire forces is to find an equation to calculate the transmittable tire forces in case of braking. So, and we propose you to use the friction ellipse depicted on this slide. The semi-minor axis of the friction ellipse corresponds to the lateral tire force without braking, whereas the semi-major axis length of the ellipse corresponds to the maximal transmittable longitudinal tire forces. And as can be seen, in case of braking, a current longitudinal tire force is transmitted, and this leads to a reduction of our lateral tire force. So, and this correlation can be calculated by means of the equation of an ellipse. So, and on the next slide, I'm going to explain, I want to focus on the calculation of the lateral tire force without braking. And if you're interested in the calculation of the other tire forces, I'll invite you to the poster session after lunch. Okay, the lateral tire force without braking. We propose to use an arctangle function in order to approximate the tire forces. You can see here on the lower graphic the match of this approximation. In black, you can see the black curve corresponds to measured tire characteristics, and the green curve illustrates now our approximation. And you can see both curves fit quite well. You also see a commonly used linear tire model, which is only valid for very small slip angles. And please note that by means of modeling the lateral tire force without braking by means of this arctangle approximation, we've got only the dependency on the side slip and the slip angle, as well as only on two further lateral tire parameter coefficients. So at the end, where we achieve a plant model of 6th order, which is highly nonlinear due to the new tire model. It's time invariant. It's time variant and has, of course, the time variant model parameters velocity as well as acceleration. It's minimal phase, unstable, has a relative degree of 4, and is controller free. So, based on this model, we designed a follow-up controller via the method of input-output linearization. And the method of input-output linearization can be, let's say, the design of this controller can be divided into 4 main steps. The first step comprises the transformation of the plant model into the Burns-Isidori normal form, and by means of this we obtain the new state vector set. The second step comprises the design of the nonlinear feedback controller to compensate for the nonlinearities of the external dynamics and to decouple the internal dynamics. And as a result of these 2 steps, we obtain the input-output behavior depicted here in the graphic. So we obtain a linearized input-output behavior. We achieve an integrated chain of the order of the relative degree of the system, and here it's the order 4. So in the next step, we superposition a linear state controller in order to stabilize the plant and furthermore to impose a desired closed loop dynamics. And the fourth and last step comprises of the application of a pre-filter, which takes now into account 4 time derivatives of the set value W. And so by means of the last step, we achieve a really precise track guidance. So now let's have a look on the experimental results. For proving our developed controller, we replicated a hazardous traffic situation with pedestrian involvement on the proving ground, which can only be diffused by a combined steering and braking maneuver. So it can be seen here in the graphic, the last point to brake as well as the last point to steer were already passed. In order to evaluate the relevance of our autonomous collision avoidance system, we firstly conducted a case study in order to analyze the normal driver's reaction. And I'm going to show now on the next slide also 2 videos according to this. The drivers were acoustically as well as optically warned at the beginning of the pedestrian's movement. The first scenario I'm going to show illustrates the reaction of an unprepared driver. And afterwards I'm going to show a scenario where the driver were prepared and they were instructed to avoid the collision by steer and brake. Afterwards I'm going to present the results of an automated evasive maneuver with simultaneous braking. I'm going to present our proposed nonlinear control scheme, and I'm going to compare the results to a linear 2 degrees of freedom controller, which, let's say, represents the state of the art. Okay, now let's have a look. The video shows now the reaction of an unprepared driver. I have to say, most drivers didn't show any reaction. And in case of showing a reaction, most of them initiated a braking maneuver. What else can be seen, the distance to the pedestrian was too short, so the collision could not be avoided by braking. So after that, we instructed the driver to avoid the collision by steering and braking. However, the driver's reaction was either too weak, as can be seen, the collision could not be avoided, or, as can be seen here in the video, the reaction was too strong. So it was a really good driver. He avoided the collision. However, he endangered the oncoming traffic. He exceeded the center line. And now let's have a look on our developed controller. You can see here in the picture sequence that on the one hand, we were able to avoid the collision with the dummy. And furthermore, we ensured a lane-keeping, evasive maneuver. And this is also proven by our measurement results. At the beginning of the maneuver, the velocity was 40 kilometers per hour. And at the point in time of passing the dummy, the velocity was reduced to 25 kilometers per hour. And at the end of the maneuver, we did not exceed the center line. Okay, now let's have some further looks. The upper left graphic depicts the y coordinate of the preview point, and you can see here in red the set value as well as in blue the measured value. And these are the results of our proposed nonlinear control scheme, which includes also the nonlinear coupling of the longitudinal and higher forces. You can see that we achieved a really precise track guidance, which also is revealed by the lower left graphic. We achieved a track guidance with lateral position errors of less than 5 centimeters. And this is remarkably low because we're achieving, because we also initiated braking maneuver during the emergency steering. You can see here on the left, on the right, the velocity as well as the control signal. So okay, now let's have a look at how a controller is working in these situations, which does not consider this nonlinear coupling. And we can see that we're not able to achieve the precision of track guidance. We got lateral deviations up to 10 centimeters, which are a result of a completely different control signal. However, it can be stated that in both cases, we reduced the kinetic energy significantly, and so, of course, the injury mitigation was achieved. We also have to state that by means of our new lateral controller, we achieved the enlargement of survival space. Okay, so now let's conclude. We developed a new lateral control scheme for the lateral vehicle guidance in combined emergency steering and braking maneuvers. To this, we derived a new vehicle model, including a nonlinear combined lateral and longitudinal tire model. And on basis of this model, we designed a follow-up controller using the method of input-output linearization. And the experimental results demonstrated that by means of our controller, further pedestrian collisions can be avoided. The focus of current research is now to implement our developed control scheme in our new research vehicle, and to this we want to adapt the control scheme to a car with serious production sensors and actuators. And furthermore, we want to develop an optimal collision avoidance strategy via automated steering and braking That means we want to include also the nonlinear coupling of the lateral and longitudinal tire forces in the path planning. So thank you for your attention, and for further discussion I will invite you to the poster session after lunch.
Thank you very much for this interesting presentation. We have time for a question.
Hello, thank you for your presentation.
Yeah.
And I have two basic questions. First of all, you argued this is a controller for combining braking and steering, but in your control plan model for control sensitivity, I didn't see the longitudinal control input like braking torque, or are you assumed you applied the maximum braking force? Or?
So there are two approaches. Of course, it would be right to model out the longitudinal vehicle dynamics and to include them in the plant model. However, this would lead to a MIMO system, multiple input, multiple output, and for we achieved here in order. We assumed here the time variance of the velocity in the model. So we've got the time varying parameter velocity as well as acceleration. And by means of this assumption, we include the longitudinal dynamics. But of course, they're not directly modeled in the
okay, you provide a speed profile as a parameter of...
yeah. So we say the velocity is a time varying parameter. We measure the velocity in each time step, also the acceleration, deceleration of the vehicle. And so the controller is adapted to the present situation. And you have to know that our new tire model here is also parameterized by means of the deceleration of the vehicle. So at the end we achieve,
but I guess in such scenario, longitudinal dynamics is also quite critical.
Yes.
Especially the delay of actuator. You need to take into account.
That's right, and that's now the focus of current research. We want to now to develop an optimal collision avoidance strategy, and that means we want to plan a trajectory comprising the dynamic limitations also of our longitudinal actors, and so we decouple also a little bit the plant models by means of our trajectory planning.
And that comes my second question. If we design a controller, we need to set the control objective. And in your scheme, what is your control objective? You track a reference or stabilize your vehicle?
Our main objective is to control, to guide the y-coordinate of the preview point along a set value, along a predefined path.
Okay, to track a predefined trajectory.
Yes. And the path is calculated in real time in case of detecting the dummy, or better say, in case of detecting a critical tracking situation.
Okay, thank you very much again, and thanks to all speakers for 4 great presentations. And this concludes the session. Enjoy your lunch.